So imagine you're cruising down the highway. You're doing maybe 70, 75 miles an hour.
Right. Just keeping up with traffic.
Exactly.
Yeah.
The radio's playing, the climate control is, keeping everything perfectly comfortable. And right underneath you, separating you from the asphalt, is roughly 1,000 pounds of highly volatile, densely packed chemical energy.
It is kind of wild when you think about it.
It really is. Most of the time, we don't even think about it, right? We just press the accelerator and the car goes.
Yeah, I mean, it's basically a localized miracle of modern engineering. We've totally normalized sitting on top of enough stored kinetic energy to power a whole neighborhood block.
But the reality of managing all that energy is actually incredibly precarious.
Yeah.
So I want to welcome you to this deep dive into the hidden, really high-stakes world of electric vehicle battery safety.
We've got a really fascinating topic today.
We do. Today, we're cracking open this massive, highly technical master playbook that automotive engineers use to keep that chemical beast under control. We are looking at one hyper-specific, genuinely terrifying fault code.
Right, the infamous P0A80.
Exactly. And just to ground this in our source material, we're focusing on the first dimension of this engineering spec, which covers the battery cell and electrochemical layer.
Yeah.
And specifically fault code 101, which is that P080 code.
Yeah, for anyone who has ever seen a diagnostic scanner plugged into an EV, seeing that specific alphanumeric sequence, it triggers an immediate sinking feeling.
Oh, I bet. What does it actually translate to?
Well, translated from the engineering shorthand, P0A80 basically means replace hybrid or EV battery pack due to a weak cell.
Wow.
Yeah, it's essentially the ultimate death sentence for a battery system.
And the reason a single, quote-unquote weak cell can just write off an entire multi-thousand-pound vehicle, it comes down to a really intuitive concept.
The barrel effect.
Yes, the barrel effect. So think of a wooden barrel made of vertical planks strapped together. If you want to fill that barrel with water, its total capacity isn't determined by the tallest plank, right? Or even the average height of the planks.
Right. It is entirely dictated by the shortest or, the most broken plank. The water simply pours out over that lowest point.
Because an EV battery pack isn't just one giant pool of energy. It's hundreds, or sometimes like thousands, of individual battery cells wired together in this massive series circuit.
Exactly. So the total power you can draw from the car and your total driving range, they are rigidly capped by the single most degraded cell in that entire chain.
Which means the entire game of EV safety and performance, really, is this massive hunt for that one weak link.
That's exactly what it is. And we're going to trace the whole life cycle of this P0A80 failure today.
Right. We want to understand how a microscopic defect forces a massive vehicle to shut down. Like how the vehicle's computers act like detectives to find that defect in milliseconds.
And of course, the extreme lengths that factories go to just to prevent it from happening in the first place.
So let's start down at the absolute microscopic level. Because before the car's computer can flash a warning light on your dashboard, this quiet sabotage is happening inside the cell itself.
Down in the electrochemical layer.
Yeah. When a cell goes rogue and becomes that weak plank in the barrel, what is actually happening physically?
Well, to understand that, we have to look at the internal architecture of a cell. At its core, a battery is just tightly wound or stacked layers of positive material and negative material.
Okay, pretty standard.
Right. But they are kept apart by this incredibly thin, porous plastic membrane called a separator. The entire function of the battery relies on that separator keeping the positive and negative sides from touching physically.
But it still has to let the energy through, right?
Exactly. It allows lithium ions to pass through these tiny microscopic pores.
So it's basically a physical barrier, but a chemical doorway.
That is a great way to put it, yeah. Now, the first major cause of a weak cell is what engineers call a microshort. And this is often triggered by a manufacturing defect, like a metallic burr.
Like the sharp flakes left behind when you cut a piece of aluminum.
Just like that, but, microscopic. When massive industrial blades slice the giant rolls of metal foil used for the electrodes in the factory, they can leave behind this tiny metal flake. And if that flake evades the factory filters and ends up inside the cell, it just sits there. Over months of driving, as the car vibrates over potholes, and as the battery cell physically expands and contracts every single time you charge and discharge it.
It's moving around.
Exactly. That tiny metal burr acts like a needle.
So it's slowly working its way through that plastic separator over time.
And when it finally pierces through, it establishes a physical bridge between the positive and negative sides. This is your microshort.
Wow.
Yeah, it creates a high-resistance pathway where energy can just constantly leak across. So even if the car is parked in your driveway for a week, completely turned off, that specific cell is quietly bleeding energy through that tiny metal bridge.
It creates a high self-discharge rate. So the barrel has a leak. But I mean, manufacturing defects are only one part of the story, right? Because I know how we actually drive and charge the car also plays a massive role.
Oh, absolutely.
There's this phenomenon called lithium plating that the spec talks about. It happens when people try to fast charge their cars in freezing temperatures.
Yeah.
What's the actual physics behind that?
Well, this is actually one of the most critical electrochemical bottlenecks in the technology. So the negative electrode is usually made of graphite. Think of it as a rigid sponge.
Okay.
When you plug the car in to charge, you're basically forcing lithium ions to swim over to that graphite and embed themselves into the empty spaces of the sponge.
The technical term is intercalation, right? The ions slotting into the graphite structure.
That's it, yeah, intercalation. But temperature dictates the speed of everything. When it's freezing outside, the electrolyte fluid inside the battery gets very viscous.
It gets thick and slow.
Right, everything slows down. The graphite sponge becomes stiff, and it physically cannot absorb the lithium ions quickly enough.
So I pull up to a massive 350 kilowatt DC fast charger in the middle of January, and I force all this electrical current into a freezing battery.
Yeah.
The ions are rushing toward the graphite, but the door is basically jammed.
Exactly. The lithium ions just pile up on the surface of the graphite, and because they can't get inside, the local voltage potential drops outside of the safe electrochemical window.
Oh, so they change form.
Yeah, instead of staying as ions and sliding into the sponge, they bond with available electrons right there on the surface and turn back into solid metallic lithium.
And that is lithium plating.
That's lithium plating.
And having solid metal crystals growing inside a tightly packed battery cell. I mean, that sounds catastrophic.
It is, mostly because they don't grow in nice, smooth, flat layers. They grow as these jagged, microscopic stalagmites called dendrites.
Just like a cave?
Yeah, and just like the metal burr from the factory floor, these sharp dendrites grow outward until they spear right through the plastic separator.
So you end up with a microshort again.
Exactly. But this time, it wasn't a factory error. It was entirely induced by the environment and, the charging habits.
So whether it's a factory burr or winter fast charging, we have physical punctures causing the cell to constantly bleed energy. But the spec sheet goes into another layer of degradation that focuses on chemical stress.
Right, the chemical aging process.
Yeah, it refers to two acronyms, LLI and LAM, loss of lithium inventory and loss of active material. Walk us through how these effectively shrink the battery's capacity.
So to understand LLI, we need to introduce a crucial component called the SEI, or the solid electrolyte interface.
Okay, what was that?
Well, the very first time a battery is charged at the factory, a tiny amount of the electrolyte fluid actually decomposes. It forms this thin protective crust on the surface of the negative electrode.
Kind of like a scab forming over a scrape.
That's actually a very powerful visual. That crust, the SEI layer, is completely necessary because it stops the rest of the electrolyte from constantly reacting with the electrode.
Right, it protects it.
But here's the problem. When a cell is under extreme stress, maybe from extreme heat or from the continuous energy drain of a microshort, that protective crust starts to thicken permanently.
And as it thickens, it's absorbing materials from the battery itself.
Exactly. It literally consumes the active lithium ions. They get permanently trapped inside this expanding crust, locked away where they can never be used to store or release energy again.
Well,
And that is your loss of lithium inventory. The total number of available workers carrying the electrical charge back and forth is just permanently reduced.
okay, so if LLI is losing the workers, what is the loss of active material, the LAM?
If LLI is losing the workers, LAM is the destruction of the workplace.
Oh, man.
Yeah. The graphite sponge we talked about, it isn't indestructible. As lithium ions forcefully jam themselves into the structure and then get violently ripped back out during heavy acceleration, it creates mechanical strain.
It's wearing out the sponge.
Over time, or under severe stress, the actual graphite particles develop these microscopic cracks. And when a particle cracks, parts of it become electronically isolated from the rest of the cell.
It basically becomes dead weight.
Completely useless. You lose the lithium ions to the crust, and you lose the graphite structure to microcracking. The physical macroscopic result is that the total capacity of that specific cell shrinks dramatically.
So a cell that might have started as a 100 amp hour cell, it can now only hold maybe 60 amp hours.
Exactly.
Let's pull back from the microscopic chemistry for a second and look at the physical layout of the battery pack.
Yeah.
Because the environment inside that massive metal box under the car plays a huge role here.
Oh, thermodynamics are everything.
Right. The concept of hotspots comes up frequently in this failure analysis.
Mm-hmm.
How do they form, and why are they so dangerous?
So hotspots are localized areas within the battery pack that operate at a slightly higher temperature than the surrounding areas, and they can form for incredibly mundane physical reasons. Well, a liquid cooling channel might have a slight bend in it that creates uneven flow. Or the thermal paste, the material designed to transfer heat from the cell to the cooling plate, it might have a tiny microscopic air bubble in it.
So it just doesn't cool as effectively in that one spot.
Exactly. Or perhaps one specific cell is just physically positioned a little too close to a high voltage contactor or a fuse that naturally generates its own heat.
But, I mean, we aren't talking about a cell being on fire here. We are talking about slight temperature variations. I read a metric in the spec that completely blew my mind. It said a temperature gradient of more than 3 degrees Celsius across the entire pack is considered a critical danger zone.
Yes, 3 degrees.
3 degrees. I mean, if my living room is 3 degrees warmer than my kitchen, I barely even notice. Why is 3 degrees a death sentence for an EV battery?
It all comes down to physical chemistry, specifically a principle known as the Arrhenius equation.
Okay, bringing in the equations.
Just one. This equation basically models how the rate of chemical reactions changes with temperature. And the key takeaway here is that the relationship is not linear, it is exponential.
Oh, so a cell that is 3 degrees hotter isn't just aging a tiny bit faster, it's aging vastly faster.
Vastly. The heat aggressively accelerates the thickening of that SEI layer we just discussed, and as that crust thickens, it creates a physical roadblock for the energy trying to get out.
It's harder for the energy to move.
Right. We measure this as DCIR, direct current internal resistance. So the hot cell's internal resistance spikes.
And high resistance means the cell has to work much harder to push the same amount of power out.
Exactly. And when it works harder, it generates even more internal heat.
So it's a vicious cycle.
A completely self-sustaining loop. Under a heavy load, like if you're merging onto a highway, a cell with high internal resistance will experience a massive voltage drop. It simply cannot push the electrons out fast enough through all that thickened chemical crust.
Okay, if we synthesize all of this, the microshorts, the SEI thickening, the hotspots, it actually reminds me of a very specific analogy.
Let's hear it.
Imagine a marathon relay team, 100 runners strong. But instead of just passing a baton, they are all physically tied together at the waist with a short rope.
Okay, so that represents our series circuit battery pack. I like this visualization. They all have to move at the exact same speed.
Right. Now imagine one runner gets a sharp piece of gravel in their shoe right at the starting line.
Mm-hmm.
That's our metal burr, causing a microshort. It's painful, so they are bleeding energy just trying to keep pace.
Yep, the self-discharge.
Furthermore, this specific runner happens to be wearing a dark shirt in the direct sun. So that's our hotspot. Because they are hot and struggling, their ankle starts to aggressively swell up.
And that's the SEI layer thickening and the internal resistance spiking.
Yes. And because they're tied to everyone else, every single time the team tries to sprint, this one runner with a swollen ankle stumbles and just pulls the whole line back.
That is a perfect way to describe a voltage drop under load.
And eventually, that one runner completely collapses on the pavement. Because of the barrel effect, the entire 100-person team is violently forced to a dead stop.
They have no choice.
Right. It literally does not matter if the other 99 runners are perfectly hydrated, deeply rested, and ready to run another 20 miles. The weak link has broken, and the vehicle is dead.
Which naturally begs a massive logistical question.
Right. How do you find the guy with the bad ankle?
Exactly. If one single failing cell out of hundreds can bring down the entire vehicle, how does the car's brain detect that one specific bad apple? You're driving down the highway, you're drawing wildly fluctuating amounts of power to accelerate, brake, run the heater. The voltages of all the cells are just bouncing up and down constantly.
It seems like trying to find a specific irregular heartbeat while the patient is sprinting up a flight of stairs. Like, how does the diagnostic software cut through all that noise?
Well, the detective work relies on a highly sophisticated layer of hardware and software working in tandem. The frontline hardware is a component called the AFE chip, the analog front end.
The AFE chip.
Right. These are specialized automotive-grade microchips whose sole existence is to measure voltage. They relentlessly interrogate every single cell in the pack, taking highly precise voltage readings in milliseconds.
So they are basically just machine gunning questions at the cells, like, what's your voltage? What's your voltage? Thousands of times a minute.
Exactly. And they stream this massive fire hose of data back to the BMS, the battery management system. The BMS is running continuous filtering algorithms looking for specific mathematical deviations.
What kind of deviation?
The baseline trigger for suspicion is if a cell's voltage deviates from the pack average by greater than or equal to zero point 0.3 volts, or if it crosses a 20% safety threshold.
Okay, I have to pause on that number. 0.3 volts. A standard AA battery in my TV remote is 1.5 volts. 0.3 volts sounds like a rounding error. Why is the system hyperventilating over a fraction of a volt?
Because in the lithium-ion chemistry used in EVs, the working voltage window is incredibly tight. It's usually between roughly 3.0 volts empty and 4.2 volts completely full.
Okay, that is tight.
And the discharge curve is mostly flat in the middle. So a deviation of 0.3 volts doesn't just mean a slight imbalance. It means that cell is operating in an entirely different state of charge compared to its neighbors. It is massively out of sync.
But again, if I slam on the brakes to regenerate power and then I just floor the accelerator, every cell's voltage is swinging wildly. How does the BMS know cell number 45 is actually dying and not just momentarily lagging behind due to, I don't know, a sensor glitch or a sudden power draw?
That's where the software comes in. The BMS employs what engineers call cell tracking logic. It doesn't rely on a single snapshot in time. It keeps a continuous running ledger over the entire lifespan of the battery.
So it's taking notes on everybody.
Constantly. It tags the cell with the lowest voltage, calling it cellmin V, and the cell with the highest voltage, cellmax V. It is looking for a specific behavioral pattern called the dual identity trait.
Dual identity, like Jekyll and Hyde.
More like a bucket that has physically shrunk. If cell number 45 is always the absolute first cell to hit the minimum voltage limit when you are driving and draining the battery, and it's also the absolute first cell to hit the maximum voltage limit when you plug the car in to charge.
Oh, the capacity has physically shrunk. The Lamb we talked about earlier,
Yeah.
it's no longer a 100-gallon tank like its neighbors. It has chemically decayed into a 50-gallon tank.
Precisely.
So if you drain all the tanks at the same speed, the small one empties first. And if you fill them all at the same speed with the charger, the small one overflows first.
That is the smoking gun. If the software confirms this dual identity over a sustained period, it systematically rules out sensor drift or temporary noise. The algorithm flags cell 45 as a confirmed physical weak cell, accumulating internal deterioration scores against it in the system memory.
Let me push back on this, though, because any computer system can make a mistake. What if the wiring harness connected to cell 25 just got jarred when I hit a massive pothole? Or what if there's electromagnetic interference from a power line messing with the AFE chip? Does my car suddenly throw a permanent P0A80 code and tell me I need a $20,000 battery replacement over a bumped wire?
Absolutely not. Automotive engineers are deeply paranoid about false positives, largely because of that exact warranty cost you just mentioned.
Right, they don't want to pay for that.
Exactly. So the system is explicitly designed to demand a second opinion. Before the BMS etches that permanent P0A80 code into the vehicle's non-volatile memory, it actively attempts a software-driven medical intervention. It tries to heal the battery.
Wait, it tries to heal a physical microshort. How? You can't unpierce a separator with software.
No, you can't. But the system has to absolutely prove the issue is physical damage and not just a temporary consistency imbalance.
Okay, what is a consistency imbalance?
Sometimes perfectly healthy cells just get slightly out of alignment in their charge levels. So the car waits until you are safely parked and plugged into an AC slow charger at home. Then the BMS initiates a maintenance balancing request.
It waits for a safe, low-stress environment. What does the balancing actually do?
It forces the onboard charger to stay active in a trickle charge state much longer than normal, and simultaneously it activates the passive balancing circuits.
Okay.
These are tiny physical resistors built onto the circuit board above the cells, connected to the strong, full cells. The system intentionally bleeds off a small amount of electrical energy from the healthy cells, turning it into heat.
Wait, so it's purposefully wasting energy from the good cells?
Yes. By bleeding the strong cells, it creates headroom, allowing the charger to keep pushing a small trickle of energy into the entire pack, with the goal of manually forcing the lagging weak cell to catch up to the rest.
Oh, it gives cell 45 extra time and extra juice.
Yes.
So it's basically like pausing the marathon, So the runner with the swollen ankle can hobble up to the rest of the team.
That's it, exactly. The BMS will run this deep balancing routine over several charge cycles, but, and this is the critical juncture, if after multiple interventions the voltage difference is still massive.
The blueprint defines the failure point as, what, the maximum voltage minus the minimum voltage remaining greater than a set failure threshold.
Yes, exactly. And more importantly, if the voltage of cell 45 instantly plummets the second you put the car in drive and demand power.
Then the jig is up. The software intervention failed. The system knows beyond a shadow of a doubt that the microshort is real, the internal resistance is permanent, and the capacity is gone.
That is the point of no return. The BMS writes the confirmed P0A80 code directly into the EEPROM or flash memory.
So it's permanent.
The diagnosis is locked, the warranty claim is inevitable, and the vehicle shifts immediately into a defensive posture.
Which brings us to a terrifying reality for the driver. Because the car has just realized that one of its internal components is irreversibly damaged and poses a severe thermal runaway risk. A chemical fire. What does the car do at that exact moment to keep the humans inside alive?
Well, the primary directive of the BMS at this stage is locking out the most extreme dangers. The very first non-negotiable rule when a P0A80 is confirmed is that DC fast charging is immediately and permanently prohibited.
So you are locked out of the supercharger network completely.
Absolutely. The logic is simple and brutal. Shoving 400 volts and hundreds of amps of direct current into a cell that has a thickened SEI crust and a microscopic metal short, it's a guaranteed recipe for localized superheating.
It would just cook it.
It would accelerate lithium plating exponentially, trigger internal boiling of the electrolyte, and initiate thermal runaway. The car's software will electronically handshake with a fast charger, identify its own fault, and simply refuse to close the contactors to accept the charge.
Okay, denying a fast charge makes total sense. But what if this permanent fault is confirmed while I am actively driving down the interstate at 70 miles an hour? Does the car just cut the main power contactors and leave me coasting with no power steering in the passing lane?
No, suddenly severing all propulsion power at highway speeds is incredibly dangerous. Functional safety standards require a structured, predictable degradation of performance.
Okay, so step down.
Right. Instead of shutting off, the car enters a multi-stage dynamic derating phase. The first thing you experience as a driver is a visual and tactile warning. The dashboard will illuminate with a red or yellow malfunction indicator lamp, and typically you will see the infamous turtle icon.
The turtle light. It's universally recognized as you are in serious trouble.
The turtle icon means the BMS has initiated dynamic power derating. It actively recalculates the state of power, which is the maximum safe limit for electrical current, and it slashes it.
By how much?
In derating stage 1, the maximum available propulsion power is instantly capped at 50% of its normal limit. If you have the accelerator pinned to the floor, the car will feel incredibly sluggish.
It's basically emergency medical triage for a machine. The vehicle recognizes it's at immediate risk of a catastrophic event, essentially a thermal heart attack. And instead of letting you continue to sprint, it physically restricts your output, forcing you into a slow, highly monitored walk just to ensure you survive long enough to reach a mechanic.
That's a very accurate translation of the engineering intent. But, if the cell continues to destabilize, the car will take even more aggressive control. Let's say the voltage of cell 45 drops off a cliff, crossing the extreme undervoltage protection threshold. The blueprints often set this around 2.5 volts.
At 2.5 volts, the cell is practically dead. What happens then?
The BMS triggers the ultimate failsafe. It dictates that purely electric driving must be rigidly and entirely disabled. If the vehicle is a hybrid, the BMS sends an emergency priority message over the CAN bus to the VCU, the Vehicle Control Unit.
And what does the VCU do?
The VCU takes over and forces the vehicle into an HEV limp-home mode.
So it locks out the high-voltage battery entirely and relies solely on the internal combustion engine and the small generator to physically move the mass of the car.
Yes, and it severely restricts the output of that combustion system, usually capping the vehicle's speed to a crawl, like 50 kilometers per hour or less.
Which is roughly 30 miles an hour.
Yeah.
You cannot maintain highway speeds. You are forced onto the shoulder or onto local roads. It's an incredibly aggressive intervention.
It is.
The car is prioritizing the absolute prevention of a high-voltage fire over everything else, including your ability to get home on time.
It is prioritizing human life. Replacing a battery pack is expensive, yes, But replacing a vehicle that burned to the ground with occupants inside is unacceptable.
And speaking of that expense, replacing an entire high-voltage battery pack under warranty is a massive financial nightmare for a manufacturer.
Yeah.
We are talking 10, 15, sometimes $20,000 per vehicle.
E-
I have to imagine automotive manufacturers pour massive resources into ensuring this specific P0A80 code never actually triggers in the real world. How do they design the physical battery pack to prevent these thermodynamic and electrochemical cascades from starting?
Well, this takes us into the realm of DFMEA, which stands for Design Failure Mode and Effects Analysis.
DFMEA.
Okay. It's a formalized engineer methodology used to map out every single way a product could fail, and then design structural mitigations against those failures right in the blueprints. In the DFMEA matrix, P0A80 is universally assigned a severity score of 8.
A severity 8 on a scale of 1 to 10.
Correct. An 8 indicates a critical safety and functional issue that degrades the core operation of the vehicle, requires a high-cost intervention, but typically includes warning systems before a complete loss of life safety.
So because the severity is so high, the prevention strategies built into the blueprint must be massive.
They are. We established earlier that heat, specifically hot spots triggering the Arrhenius equation, is a primary catalyst for cell degradation.
Right.
So how do you design a metal box filled with hundreds of heat-generating chemical pouches so that no single pouch gets hotter than the others?
I have no idea. How do they do it?
You have to master the invisible physics of fluid dynamics. Battery engineers utilize massive supercomputers running CFD, computational fluid dynamics, to model the exact physical behavior of liquid coolant as it flows through the microchannels underneath the battery cells.
So it's not just a matter of slapping a radiator on it and pumping cold water through a tube.
Not at all. The design must be perfectly symmetrical in its thermal extraction. The engineers iterate the geometry of the cooling plates millions of times to eliminate what they call flow dead zones.
Flow dead zones, like where the water just sits.
Exactly. Areas where the coolant might stagnate for even a fraction of a second, absorbing too much heat. The engineering mandate is to guarantee that the temperature gradient across the entire volumetric space of the pack remains under that 3 degrees Celsius threshold we talked about earlier.
Regardless of whether you are parked in the blazing sun or towing a trailer up a mountain. So if they can maintain that thermal symmetry, they eliminate the localized exponential aging. The whole marathon team ages at the exact same predictable rate.
Precisely. That handles the thermodynamic prevention, but they also attack the electrical prevention. We discussed the car's attempt to heal itself using passive balancing circuits during AC charging, right?
Yeah, bleeding the energy is heat.
At the design phase, engineers run a WCCA, a worst-case circuit analysis. They model the absolute harshest conditions those tiny bleeding resistors will face, and they massively overspec the components to ensure they can handle high heat dissipation without burning out.
But I keep coming back to the inefficiency of passive balancing. It just feels so primitive. You are literally taking stored electrical energy, which the driver paid for, and converting it into useless heat just to stall for time while a weak cell charges up.
You're right. It is thermally and energetically inefficient, which is why in high-end electric vehicles or massive commercial EV trucks, the DFMEA dictates the use of active balancing circuits.
Okay, what makes them active?
Instead of bleeding off energy as waste heat, an active balancer uses complex arrays of capacitors and inductors to literally scoop energy out of the highest voltage cells and pump it directly into the lowest voltage cells.
Oh, that is so much smarter. It's like Robin Hood, stealing from the rich cells to give to the poor cells.
It is exactly like that. The blueprints specify that these active circuits must be capable of transferring greater than 1 amp of energy continuously. They actively prop up the weak cell, dynamically equalizing the voltages in real time while the car is actually driving.
Which vastly extends the time before a cell hits that fatal dual identity threshold.
Exactly.
Okay, I have to ask a question that has been bothering me since we started this whole thing. We need supercomputers running fluid dynamics to keep the temperatures perfectly even. We need complex active balancing circuits pumping energy back and forth to keep the voltages even. Why don't the manufacturers just build perfect battery cells to begin with? I mean, if every single cell was manufactured to be exactly molecularly identical, wouldn't all this complex management just disappear?
It is the holy grail of battery manufacturing, but it runs into the brick wall of physical reality. You are dealing with highly volatile chemical slurries composed of materials mined from the earth, mixed in massive vats, and coated onto microscopic metal foils at incredibly high speeds.
Right.
Achieving absolute perfect molecular consistency across billions of cells is physically impossible. The chaos of the physical world will always introduce microscopic variations.
Which means the battle isn't just fought in a CAD program by designers. It has to be fought on the factory floor. How do manufacturers hunt for these tiny imperfections, the metal burrs, the microshorts, before the cell is sealed inside a battery pack and shipped to a dealership?
So this transitions us from design to process. The PFMEA, process failure mode and effects analysis. The manufacturing environment for EV batteries is honestly closer to semiconductor fabrication than traditional automotive assembly. Yes, it requires an aggressive, unrelenting war on particulate matter. The blueprints mandate that the rooms where the cell electrodes are physically wound and stacked must meet, at a minimum, an ISO Class 6 cleanliness standard.
Give me some context for ISO Class 6. What does that actually look like?
Well, a typical modern hospital operating room might operate around an ISO Class 7 or 8 level.
Wow.
An ISO Class 6 clean room is exceptionally cleaner than a surgery room. The air is entirely replaced and heavily filtered dozens of times an hour. The factory workers wear full, sealed clean room suits.
Because if a single piece of lint or dust gets in there.
If a single microscopic speck of conductive dust or a tiny metal burr generated when the blades cut the foil falls onto the electrode before it is wound together, it will inevitably become the needle that pierces the separator.
So how do they stop the burrs from the cutting blades?
To prevent this, the automated cutting stations are shrouded with high-pressure, inline vacuums that aggressively suck away any debris the microsecond it is generated.
And I imagine they inspect the foil as well.
Continuously. They use high-speed optical pinhole detectors. These are arrays of lasers that scan every single square millimeter of the metal foil as it rolls through the machines at high speed.
Lasers.
Lasers. If the laser detects an anomaly, a scratch or a burr smaller than a human hair, that entire section of the roll is instantly flagged and rejected.
It is mind-blowing to think that the reliability of a 5,000-pound truck hinges on laser scanning for microscopic dust. But even with lasers in clean rooms, defects have to slip through. How do they test the final sealed battery cell to ensure it doesn't secretly have a micro short?
They put a cell through an interrogation phase known as formation and grading. After a cell is fully assembled, injected with electrolyte, and given its initial charge, it isn't immediately put into a car. It is placed into massive, climate-controlled warehousing chambers for days or even weeks.
And what's happening in there?
During this time, the factory computers perform a K-value interrogation.
Okay, what exactly is a K-value?
The K-value is the precise measurement of a cell's self-discharge rate while resting, and it's measured down to millivolts per day.
Millivolts per day.
The automated systems monitor the voltage of millions of cells sitting on these racks. If a cell has a microscopic metal burr causing a microshort, it will slowly bleed voltage while doing absolutely nothing.
So they are actively watching the cells bleed to identify the weak ones.
It is a ruthless 100% screening process. If a cell's K-value shows it is secretly leaking even a fraction of a millivolt more than the acceptable baseline, it is immediately discarded. It will never see the inside of an EV.
Brutal.
But the data tracking goes even deeper. Before a passed cell is assigned to a battery pack, robotic testers measure its open circuit voltage and its internal resistance, both AC and DC.
And what do they do with all that individual cell data?
They bind it to the cell's physical identity. Every single cell has a 2D barcode laser etched onto it. The factory's manufacturing execution system, the MES, takes all that test data and digitally attaches it to that barcode forever.
It essentially creates a permanent digital birth certificate and medical history for every single cell.
Yes, and engineers use that massive data set to run statistical process control, or SPC. They are constantly monitoring the mathematical stability of the production line. The engineering blueprint specifies that the process capability index, the CPK, must rigidly stay greater than or equal to 1.67.
Okay, I know a little bit about statistics, but help me ground that number. What does a CPK of 1.67 actually signify in the physical world?
In mass manufacturing, a CPK of 1.33 is widely considered the standard for a capable process. Hitting 1.67 is incredibly difficult. It signifies a Six Sigma level of quality control.
So near perfection.
It means the manufacturing process is so tightly refined and the variation between the cells is so microscopically narrow that producing a defective cell is a statistical anomaly. It ensures that the millions of cells coming off the line are as close to perfect clones of each other as the laws of physics will allow.
Because of the barrel effect. If they aren't clones, the pack fails. And even after they assemble these perfect clones together, they have to physically connect them. The blueprint mentions checking the bus bars.
Right, the bus bars are the thick, conductive metal strips welded between the terminals of the individual cells to tie them together into that massive series circuit. The specification requires that every single automated weld must be tested to ensure the contact resistance is less than 0.05 milliamps.
0.05 milliamps is functionally zero. It's a perfect connection.
It has to be perfect. If the robotic welder leaves a tiny gap, or if the weld is slightly porous, the resistance at that physical connection point increases. When you push hundreds of amps of current through a high-resistance weld, it acts like a toaster heating element. It generates massive localized heat,
Which creates a hotspot, which triggers the Arrhenius equation, thickens the SEI layer, spikes the internal resistance, and causes our marathon runner to collapse. The entire failure cycle starts over just because of a sloppy weld. It is all so interconnected.
Exactly. Every single control on the factory floor is explicitly designed to prevent the root causes we analyzed at the very beginning of this process.
Okay, the engineers modeled the perfect cooling system. The factory built the cells in a hospital-grade clean room, laser scanned the foil, measured the K value of every cell, and perfectly welded the bus bars. They did everything right. But how do the manufacturers legally and physically prove to safety regulators that if something does go wrong, the software will actually catch it?
Enter the final phase, DVP&R, Design Verification Plan and Report.
The torture testing.
This is where the theory and the software algorithms face physical reality. Before any new vehicle platform can be authorized for mass production, the validation teams have to prove the P0A80 diagnostics are infallible. They begin with virtual torture, utilizing massive HIL or hardware-in-the-loop test benches.
How does a hardware-in-the-loop test work for a battery?
They take the actual physical BMS computer, the exact brain that will be installed in the car, and they wire it into a massive supercomputer rack. The supercomputer runs a highly complex digital simulation of a car driving through a standardized test course like the WLTC, the Worldwide Harmonized Light Vehicles Test Cycle.
So the physical BMS computer thinks it is hurtling down a highway, accelerating, braking, and managing temperatures, but it's actually sitting in a climate-controlled laboratory.
Exactly. And while the BMS is managing this digital drive, the engineers actively hack the simulation. They inject malicious parameters into the data stream. They tell the BMS that one digital cell in the simulated pack, let's use cell 45 again, suddenly has a massively elevated K-value self-discharge rate, and its capacity has digitally plummeted below 70%.
So they're simulating the micro-short in the lamb right in the software.
Yeah.
What are they watching for?
They are monitoring the internal memory registers of the BMS. The software must successfully recognize the dual identity trait of the digital cell 45, and it must successfully flag it as a physical weak cell. But crucially, it must do this with absolute precision.
So no guessing.
It cannot throw false alarms for any of the adjacent healthy digital cells. The algorithm has to be a sniper rifle, not a shotgun.
And it has to find the exact broken plank in the barrel. But, I mean, a simulation is just code talking to code. Do they force the BMS to deal with real physical chemical damage?
Oh, yes. The next phase is the physical fake versus real damage test. Engineers manually construct two distinct physical battery packs. The first pack is built with a soft unbalance.
The soft unbalance, what was that?
They purposely manipulate the charge levels so that there is a 120 millivolt difference between the cells, but every cell is physically perfectly healthy. There are no internal defects.
It's a trick, a fake weak cell.
Then they build the second pack. And for this one, they literally take a precision needle and manually pierce the separator membrane of one cell before assembling the pack. They intentionally create a hard, physical microshort.
They literally build a bomb, a chemically unstable pack.
They hook both of these packs up to standard AC charging stations and let the BMS take over. The BMS has to pass a binary test. For the first pack, the one with the fake unbalance, the BMS must trigger the maintenance balancing request, actively heal the pack by bleeding the strong cells until the voltage difference is under 20 millivolts, and it absolutely must not trigger a P0A80 code.
Because if it triggers a permanent death sentence on a physically healthy pack, just because it was slightly out of sync, the manufacturer is going to bleed billions of dollars in fake warranty claims.
Precisely. But for the second pack, the one with the pierced separator, the BMS must recognize the failure of the maintenance balancing. It must see that the voltage instantly drops when a load is applied, and it must permanently lock the P0A80 code into the non-volatile memory.
And if it fails?
If the BMS misdiagnoses either pack, the entire software architecture is sent back for rewrite.
That is rigorous. But But both of those tests are relatively slow, right? They happen during AC charging.
Yeah.
What about the dynamic driving environment? The blueprint outlines one final test that just sounds absolutely brutal. The 2.0-second FTTI race. What is FTTI?
Fault-tolerant time interval. It is the absolute maximum amount of time a system can be in a hazardous state before the safety mechanisms must take full control. This is the ultimate stress test.
Massive work.
The engineers mount a physical battery pack to an industrial dynamometer test bench capable of discharging the pack at 400 amps or more continuously.
400 amps. Let's visualize that. That is simulating a fully loaded pickup truck towing a massive boat with the accelerator pinned to the floor, climbing a steep mountain pass in the middle of summer. It is the absolute maximum thermal and electrical stress the system can endure.
While the pack is screaming under this massive 400 amp load, the testing equipment artificially induces a sudden catastrophic failure. They electronically force a single cell's voltage to drop off a cliff straight down to that extreme 2.5 volt undervoltage protection limit we discussed earlier.
The marathon runner's leg just snapped mid-sprint. What happens?
A literal digital stopwatch starts. The BMS has exactly 2.0 seconds. It is a rigid, non-negotiable functional safety mandate.
2 seconds to do what?
In those 2,000 milliseconds, the AFE chip must detect the voltage drop. The BMS must filter the data and confirm the fault is real. It must rewrite the entire state of power map to limit discharge to 50%. It must permanently ban DC fast-charging contactors from closing. It must send a CAN bus message to the vehicle control unit to trigger the HEV limp-home mode to limit the vehicle speed. And it must illuminate the dashboard warnings for the driver.
2 seconds. While hundreds of amps of raw electricity are surging through the system, the computer diagnoses a failure, rewrites the car's operating parameters, initiates physical power cuts, and warns the human. The speed of that computational triage is just staggering.
Yeah.
Why is the interval so incredibly tight? Why not 5 seconds?
Because at 400 amps of current, a cell that has collapsed to 2.5 volts is generating heat at a catastrophic exponential rate. The internal resistance is acting like a furnace. If the BMS takes 3 or 4 seconds to cut the power, the internal temperature of that cell could easily cross the threshold into thermal runaway.
So it catches fire.
The cell will catch fire, vent explosive gases, and ignite the adjacent cells. The 2-second limit is the physical boundary between a safe shutdown and an uncontrollable fire.
Incredible. Now, before we wrap up, I want to circle back to something we discussed about the factory floor, because looking at all these extreme tolerance tests really frames it in a new light.
Sure. What's on your mind?
We talked about the key-value self-discharge test at the factory. The blueprint explicitly states they reject any cell that falls outside a plus or minus 3 sigma limit compared to the rest of the batch. Now, a 3 sigma statistical limit is brutally tight.
Very tight.
Doesn't that mathematically guarantee that they were throwing perfectly healthy, fully functional, brand new battery cells straight into the recycling bin simply because they were slightly different than their peers?
It is one of the most counterintuitive and brutal realities of mass battery manufacturing. Yes, perfectly viable cells are discarded every day.
I have to push back on that logic. If the cell is fully functional and holds a charge, why waste the raw materials and the manufacturing cost? Why not use it?
Because of the fundamental physics of the series circuit, the barrel effect we started with. In a high-voltage battery pack, uniformity is vastly more critical than individual excellence.
How so?
Imagine you have a batch of cells, and one cell is actually an outlier because it is better than the rest. It has a slightly lower internal resistance and a slightly higher capacity.
Wait, having a better cell is a problem.
Mm-hmm.
How can an overachieving cell be dangerous?
Because the software algorithms and the thermal management systems rely on entirely predictable, uniform behavior across the pack. If you put an excellent cell in series with 99 average cells, the excellent cell will charge and discharge at a slightly different rate.
Oh, I see.
Its voltage curve will look different to the AFE chip. The BMS might misinterpret this variance as a sensor fault, or worse, the uneven thermal generation could create an unexpected temperature gradient, a hot spot.
Oh, because it's out of sync with the marathon team, it disrupts the rhythm of the entire line, even if it's technically a stronger runner.
Exactly. In a series-wired, high-voltage battery pack, uniform mediocrity is infinitely safer and more reliable than a chaotic mix of excellence and weakness. The factory must ensure every single cell is an exact, predictable clone of its neighbors. Any deviation, even positive deviation, introduces mathematical chaos into the safety algorithms.
Uniform mediocrity is safer than a mix of excellence and weakness. That is a wild, almost philosophical concept to wrap your head around. But when the stakes are a 2-second window to prevent a chemical fire, The absolute demand for predictability makes perfect sense.
Predictability is the bedrock of functional safety engineering.
Which brings us to the end of a truly fascinating journey today. We have traced the terrifying P0A80 code from its absolute genesis.
We really covered a lot of ground.
We started with a microscopic metal burr violently cutting through a plastic membrane, and we watched cold weather force lithium ions to pile up and form metallic spikes. We saw how the car's AFE chip constantly interrogates the pack, and how the BMS software hunts for that dual identity signature of a failing cell.
The Jekyll and Hyde bucket.
Right. We watched the car prioritize human life through medical triage, aggressively derating power and forcing the driver to limp home. We explored the pristine, hospital-grade clean rooms designed to prevent these faults. And finally, we witnessed the blistering 400-amp torture tests that prove these computers can identify a failure and lock down a vehicle in under 2 seconds.
It really highlights the incredible unseen symphony of engineering. It requires electrochemistry, fluid thermodynamics, extreme manufacturing logistics, and high-speed software, all operating in perfect, orchestrated unison just to safely manage the chaos of stored energy.
It is a symphony, and I want to leave you, our listener, with a final thought to ponder that builds on everything we've unpacked today. We've spent this entire deep dive looking at how a machine's brain meticulously tracks the health of its individual components.
Down to the millivolt.
It analyzes microscopic voltage drops, initiates maintenance balancing to try and heal minor imbalances, and decisively intervenes to limit power before a catastrophic failure occurs. Imagine, for just a moment, if our own healthcare systems utilize this level of constant granular state of health tracking for human organs.
Wow, that is a profound parallel to consider.
Think about the implications. What if we had a continuous wearable battery management system for our bodies? A system capable of detecting the earliest microscopic chemical imbalances of a failing kidney or the slight resistance spike in a stressed heart, and then initiating targeted cellular-level maintenance before the organ permanently degrades or fails entirely. We look at EVs as the future of transportation. But will the future of human medicine, driven by continuous biosensors, eventually look remarkably similar to an EV battery management system? It's something to chew on the next time you plug in your car and hear those contactors click closed. We appreciate you joining us for this deep dive into the hidden world of battery safety. We'll see you next time, but for now, stay curious.